Section 3.1, defining the derivative. Recall back in the beginning of Unit 1, we talked about how calculus was designed to help us solve two problems. In this unit, we're going to start talking about the mechanisms of how to solve the first of those two problems, specifically the tangent line problem. Recall from that very section, we also talked about secant lines. We're going to let f of x be a function, p be the point a f of a, and q be the point x f of x, which will be points on the graph of f. The line that passes through p and q is called the secant line of f of x that passes through p and q. Whenever we try to find the equation of a line, we do want to know its slope. The slope of a secant line of f of x passing through the point p and q, which will denote m secant, is going to be f of x minus f of a all over x minus a, which is just the slope formula with the 2 points plugged in. An alternative way of calculating the slope of the secant line is we'll have p be the point a f of a and q be the point a plus h f of a plus h. That is going to cause our formula to become m secant equals f of a plus h minus f of a all over h. H would represent how far to the right or left point q is from p. Below you can see figures of the secant line. No matter how we define point q, whether being x f of x or a plus h f of a plus h, the secant line would be the line that passes through these 2 points, and you'll still obtain the same slope using both formulas. In this example, we're going to refresh on how to calculate the slope of a secant line and also refresh on how to find the equation of lines in general. We're going to let f of x be 3x squared plus 5. We're going to find the slope of the secant line between the values of x1 equals 2 and x2 equals 5. The first thing we should do is evaluate our function at the two x values, which means we want to find f of 2 and f of 5. F of 2 is 17, f of 5 will equal 80. So the slope of our secant line is f of 5 minus f of 2 over 5 minus 2. We've already found that f of 5 is 80 and f of 2 is 17. And when we work that out, we get that our slope of the secant line is 21. Now we're going to find the equation of our secant line. There are several ways to go about writing the equation of a line. My favorite approach is to start with the point-slope form. The point-slope form, if you recall from college algebra or from the first section of the first unit, is y minus y1, which equals m times x minus x1. In this problem here, since we're finding a secant line, our slope is going to be the slope of the secant line that we found earlier, which is 21. x1, y1 is a point that we know our line passes through. Since this is a secant line, we can pick one of 2 points. We can either pick the 2 f of 2 or the 5 f of 5. It doesn't matter which. Because the numbers for 2 f of 2 are smaller, I am going to use the 2 f of 2 point. We've already found f of 2 earlier. We know f of 2 is 17. Now we'll plug into our point-slope form. Now, the reason why I like point-slope form is it's very easy to go from point-slope form to any other form, whether it be slope-intercept or standard form. I'm going to rewrite the equation in slope-intercept form, since that is the most common equation form for our line. We'll start by distributing in the 21, and then we'll add 17 to both sides, and we get 21x minus 35. So the slope of our secant line would be y equals 21x minus 35. Try working out the point-slope form using the point 5 f of 5 to see that despite the fact the point-slope form will look different, you will still obtain the same slope-intercept form. Thanks to the limits that we've discussed in Unit 1 and our definition of secant lines, we can define what we call tangent lines. If we make q get closer and closer to p, as we defined them in the previous slide, then the secant line begins to approach what we call the tangent line. If we look at the figure below, whether we focus on the left picture or the center picture, which are both the same picture, but labeling the points based off of which formula the secant line slope you feel like using. As we make our point q closer and closer, which notice how x1 to x2, we're approaching a. Notice how our secant lines are getting closer and closer to this greenish line here, which we can see by itself on the figure on the right. This green line we refer to as the tangent line. We want to be able to define the tangent line without limits. We can think of the tangent line kind of like being a secant line where both points are the same. The issue with that thinking, though, is that the secant line slope formula requires 2 distinct points. Otherwise, we will divide by 0. However, limits give us a mechanism that allows us to get around that issue. Now, for the formal definition of the tangent line of f of x at a point A is the line that passes through the point A f of A and has the slope, which we're going to denote as m tangent, which will be the limit as x approaches A of f of x minus f of A all over x minus A. Or it's the limit as h approaches 0 of f of A plus h minus f of A all over h. The way we can interpret the limit here, whether x is approaching A or h is approaching 0, is that is representing q getting closer and closer to p until q and p are essentially the same point. And this is what allows us to think of tangent lines as a secant line of a single point. Now, because limits always give us a unique value when they exist, we can define a function for tangent lines that we're going to discuss later in the next section. For right now, we're going to use f prime of a to represent the slope of the tangent line at x equals a. In our next example, we're going to let f of x equals 2x squared minus 4x. We're going to start by finding the slope of the tangent line of f of x at x equals 2. Now, for problems like these where we're just trying to find the slope of a tangent line at a single point. The first definition we saw, which is the limit as x approaches a of f of x minus f of a all over x minus a, is typically the quicker approach. The second formula that is used to calculate the slope of the tangent line is better for when you're defining the slope of the tangent line as a function, which we're going to discuss in a later section. But that second formula with the difference quotient does have a lot more uses when we define the slope of a tangent line of a function as a function itself. Now in this problem here, since we're trying to find the slope of the tangent line at x equals 2, that means our a is equal to 2, which means we're trying to find f prime of 2, which equals the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. F of x is our function, 2x squared minus 4x. After plugging 2 into our function, we get that f of 2 is 0, and our denominator is x minus 2. One thing to note, anytime we try to do direct substitution with these limits to find the slope of the tangent line, we are always going to get 0 over 0. So we are going to have to try to use the techniques we learned in the previous unit to try to rewrite this quotient. In the numerator, when we subtract 0, we get 2x squared minus 4x all over x minus 2. Since this is a rational expression we're trying to take the limit of, we'll try to factor, cancel out factors, then we can direct sub, and we get 4. So the slope of our tangent line is 4. Now that we have the slope of our tangent line, we can find the equation of our tangent line. Now, just like with secant lines, we do want to find our slope, which here would be the f prime of 2, which is 4. And we also need a point that our line will pass through. Since our line is the tangent line of f of x at x equals 2, that means our tangent line is going to pass through the point 2, f of 2, which is the point 2, 0. Now we can set up our point slope form, which is y minus y1 equals m times x minus x1, which is y minus 0 equals 4 times x minus 2. Y minus 0 is just y. And on the right, we'll distribute the 4. And we have y equals 4x minus 8, which would be the slope-intercept form of our tangent line. Next, we're going to estimate the slope of the tangent line from the graph at the indicated point. These kind of problems can be rather difficult to do just by looking at the graph and trying to eyeball everything. I would highly recommend, if you're working out these kind of problems online using MyOpenMath or Pearson's MyMathLab or even WebAssign, I would strongly recommend taking a screenshot of the graph and posting it into Microsoft Paint or some sort of picture editor. To help us approximate the slope, I want to draw a secant line where my second point is very close to the indicated point 2, 2. So let's say I pick that point that I have drawn in green as the second point to form my secant line. Now I want to draw a line that passes through the 2 points to represent my secant line. And there is my secant line in blue. Because of how close these 2 points are, the slope of the secant line is going to be approximately equal to the slope of my tangent line. If I take a look at this point here, which lies on my line, if I figure out the rise and the run to figure out my slope, I can see that the rise would be 2, which means the numerator of my approximation for the tangent line is 2, and my run is 1. So my tangent line is going to have a slope that's approximately equal to 2 over 1, which is 2. So again, to find an approximation for the slope of our tangent line, you do want to make a secant line where the second point is very, very close to the indicated point. And it is very helpful to put the picture of our graph in a photo editor like Microsoft Paint. There are quite a few different applications for secant lines and tangent lines. We talked about this a little bit in the first unit. Recall that the secant line of f of x between x1 and x2 is the average rate of change of f of x on the interval x1 and x2. The slope of the tangent line of f of x at a represents the instantaneous rate of change of f of x at x equals a. Instantaneous rate of change represents what the rate of change is when we're only considering that moment. The best way to think about average rate of change versus instant rate of change. Average rate of change considers the rate of change of an entire movie from beginning to end. The instantaneous rate of change is referring to the rate of change when we're only looking at one frame of that movie, not the entire film itself. A lot like when you're driving a car looking at your speedometer. Your speedometer tells you how fast you're going at that instantaneous moment. It doesn't account for any time you braked or sped up. It's just how fast you're going at that moment. A classic example of rate of change is velocity. We're going to let s of t be a position function of an object that's moving along a coordinate axis. In other words, s of t represents the position of an object if we think of the object being on a number line. And on that number line, it has 2 directions. Oftentimes, we can think of it as going left or right, or we can think of it as going up or down. But it only has 2 directions it can travel in, and those directions are along a straight line. The average velocity of the object over some time interval, which we'll either have as a of t or t of a, depending which is larger, is just the average rate of change of position, which would be s of t minus s of a all over t minus a. And we'll denote that as v average. This is typically how we calculate velocity when we're first introduced to the idea of it. We would know the position of 2 objects and at what time those 2 objects were at those positions. And we would take how far the object traveled divided by the change of time, and we say that was the velocity. However, that is only the average velocity. Within that motion, For example, if you're driving, your velocity may fluctuate. There might be some places you speed up, maybe some spots you slow down. To figure out the instantaneous velocity of an object at t equals a, that is going to be denoted as v of a, and that's going to equal s prime of a, which is the limit as h approaches 0 of s of a plus h minus s of a all over h. The instantaneous velocity would represent how fast your car is driving just in that frame of t equals a. One thing to note, oftentimes instead of saying instantaneous velocity, we'll just simply say velocity. When we simply say velocity, we are referring to instantaneous velocity. If we want to refer to average velocity, we will say average velocity. So anytime you hear the word velocity without the word average or instantaneous, assume that it is instantaneous velocity we're referring to. In our next example, suppose two vehicles start out traveling side by side along a straight road. Let f of t equal 1 minus 1 over t plus 1 and g of t equal the square root of t be position functions of the two vehicles, where f of t and g of t are measured in meters and t is in seconds. Which car is traveling faster at t equals 0.25? If we think about what the question is asking us, when we hear the word faster, that is referring to a rate of change. Specifically here, when we're talking about the rate of change of position, we are looking at which car has the greatest velocity. Now, what kind of velocity are we talking about? Instantaneous or average? Because we don't see the word average, nor do we have a time interval that we're considering, we are referring to the instantaneous velocity, which means we want to find f prime of 0.25 and g prime of 0.25. We'll start with f prime of 0.25, which would equal the limit as t approaches 0.25 of f of t minus f of 0.25 all over t minus 0.25. F of t is 1 minus 1 over t plus 1. F of 0.25 is 0.2. And if we simplify the numerator, we have the limit as t approaches 0.25 of 0.8 minus 1 over t plus 1 all over t minus 0.25. In order to resolve the 0 over 0 issue, because we have a complex fraction, we'll clear the denominators by multiplying the numerator and denominator by t plus 1. In the numerator, we'll distribute, since we're trying to get rid of the complex fractions, which gives us 0.8 times the quantity t plus 1 minus 1. As for the denominator, because we're trying to cancel out the t minus 0.25, we'll keep our denominator factor. In the numerator, we'll distribute the 0.8 and collect like terms, which gives us 0.8t minus 0.2 in the numerator. Now, I stated earlier, our goal was to try to cancel out the t minus 0.25. So in the numerator, to try to get that factor of t minus 0.25, let's try to factor out the 0.8. That's because when I factor out the 0.8, the other factor is going to have 1 as the coefficient of t, just like the coefficient of t in the t minus 0.25. And our numerator will become 0.8 times t minus 0.25. T minus 0.25s cancel. Then we can apply direct substitution, which gives us 0.64. So our f prime of 0.25 is 0.64. Next, we're going to find g prime of 0.25, which from the definition equals the limit as t approaches 0.25 of g of t minus g of 0.25 all over t minus 0.25. G of t is square root of t. G of 0.25 is 0.5. Here, in order to resolve the issue of 0 over 0, because we have square roots, we will rationalize the numerator by multiplying top and bottom by the square root of t plus 0.5, which is the conjugate of the square root of t minus 0.5. In the numerator, when we expand, we get t minus 0.25. In the numerator, just like before, since I do want to try to cancel out that t minus 0.25, we'll keep the denominator factored. Now we can see the t minus 0.25s cancel, which gives us the limit as t approaches 0.25 of 1 over the square root of t plus 0.5. Through direct substitution, we get 1. So g prime of 0.25 will be 1. So from the two vehicles, which one is moving faster? Since our g prime of 0.25 is greater than our f prime of 0.25, then the car whose position function is g of t is the faster car.